Ladies and gentlemen, and all research online, good morning. My name is Lingfeng Pan, come from Wuhan Institute of Technology, China. Today, I'm glad to be here to introduce our recent work, accelerated degradation of 316L1 under stress-assisted corrosion in oxygen-saturated liquid sodium. As we all know, energy is the basement of the modern industry. Maybe I can say no energy, no industry. And with the advertisement of nuclear energy technology, the nuclear power has become an important method of generating clean energy. And you can see in this work, we focus on the sodium cold fast fall reactor, which is one of the generation 4 nuclear system. Exactly what I only want to say, it should be claimed that safety is always the most important thing in nuclear around the nuclear power glowing. And in the past time, several nuclear accidents like Chernobyl, the 3 Mile Island, and Fukushima had occurred. And in the although some previous work have investigated the microstructure and the mechanical properties of 316 stillness there after exposed to liquid sodium, but we should know in the true nuclear system, liquid sodium is only the one condition. High temperature and loading are always working together. So in this work, we think we should consider how does the stress corrosion interaction occur under high temperature sodium, and what's the mechanism in this condition. So based on the program, we use the 316L1 cold load round bomb, which is D equals 18 millimeter, and by the result for the DBSD, you can see the green size is about 10 micrometer, and then the material is no off-field texture. Next, we design some the two types specimen. In this picture, in this picture, you can see specimen A and specimen B. Specimen A is do the creep test in L, and specimen B is do the creep test in sodium. And besides, we also need 2 main equipments in our work. You can see in this equipment 1 is the static sodium corrosion equipment, and the equipment 2 is the creep equipment adapted for sodium. You can see in the picture after creep test in sodium, the specimen are all surrounded the sodium. You can see in this picture, and use this material, specimen, and the equipment. We do 3 series experiments. They are creep in sodium and creep in L, and the static corrosion in sodium. Okay, that's the result I show you. You can see in the 9 pictures, they are all creep life in sodium and L. A2E is the creep behavior in sodium, and F2I is the creep behavior in L. And we put the creep life into this picture, and you can see and compare it with the RCC standard and other papers. You can see at the high stress in this zone, and the difference in creep life between different environment are not significant in this zone. And when the stress level decrease, you can see the creep life of specimen in the sodium environment repeats decline. Even the even the two points are below the design cover in RCC standard, is very dangerous here, I think. And now I show you the creep life and creep rate of the specimen in sodium. And by the Arrhenius equation, you can see the creep rate to the stress relationship is near linear. And I can say there is no significant difference in the stress exponent n in that chapter. Although there are different environment, and it implied that the sodium corrosion affects the rupture life and failure mechanism, but not the creep deformation mechanism. And so in this slide, I show the creep fracture surface. You can see this picture is the creep fracture surface on the sodium at 300 degree and 75 megapascal. And in the left picture is the creep fracture between air environment and sodium environment. We can see the section shrinkage of 316 Ln in sodium is lower than that in air. And besides, on the sodium, the specimen fracture short mixed fracture model. You can see in this in the left one figure B. You can see the figure model in this one. Okay. Okay. Now in this slide, I show the the element distribution and of the specimen after static corrosion. In this one, you can see the near the specimen space. We define the zone to oxide zone and affected zone, and we do the participate and XRDM lines. You can see in these two parts. It means sodium corrosion, casual participation of elements, and cracking occurs at the green boundaries. In this figure, you can see crack occurred at the green boundary, and carbide participation occurred at green boundary in that picture. You can see with carbide types identified as MC and maybe M23 C6, and sodium corrosion causes Austin to ferritin in this XRD analysis. You can see. Now, this slide shows when loading working. We compared the result in L and in sodium, and EDS mapping results show like that. I can see in this. We can see in this slide under the coupled effect of stress and sodium integrate integrate cracking intensified and element participation accelerates. You can see in this zone layout be more long in the picture. And based on all results we do, we try to predict the depth of corrosion layer. When we do this part, there are two main questions confuse us. The question one is previous model will be suitable in this way. We compared with the right point. Oh, funny. The right point is the experimental result, and the black dot line is the cursed model. We can see there are two conservative and we modify this model and do a physical-based approach to fit this result. You can see in this equation. And question 2 is how to consider the stress effects. Yeah, you can see in this picture, the black dot is the result with in sodium without loading, and the red dot is the depth of corrosion layer that with loading. This equation can't fit the results that with loading very well. So we include a term that we call the accelerate element diffusion in the blue parts, and now put the accelerate element diffusion into our model. You can see in this one is new equation, and in the 3D figure you can see we can by this new model we can predict the depth of corrosion layer very well when loading or without loading. Now let's just a simple conclusion. You can see in these two picture. Picture A is show the sodium conclusion without loading, and when the loading working, you can see just like picture B. Oxide zone and effect zone are all are together increased, and it induce the corrosion maybe more I say high. Now it shows the selective participation of elements induce phase transformation and tunnel formed on the specimen surface, and the corrosion layer collapsed and propagated along grain boundaries, and string enhancing the element diffusion, accelerate Clark propagation. Okay, that's all I want to show you. Thanks for your attention. If you are also interested in our work, please let me know, and you can email to us. We are looking forward to you. Thanks again. Thank you.